Yeah, no.
Okay. Okay, I'll say good evening, everybody. We nearly forgot to record, but fortunately, Harriet reminded me, so she will get some extra bonus points somewhere.
Thank you.
So tonight we're going to look at estimation, and the goal is to describe a single population. And with estimation, we've got a full population, and we say what we want to do is just draw a sample. I'm just revising for all the people that's not been here before. So we've got a full population. We're just going to draw a sample, do the calculation for that sample, and through that want to say something about the population. I've used the example of the average reading and writing score for all the students in Australia for grade 12. And say, for example, we want to know, and somebody says, how good is the students in Australia? Well, I obviously haven't got access to everybody, or maybe I don't. I might say, okay, I'm just going to draw a sample. I'm going to draw a sample of about 100. Remember, more than 30, the key word is 30. More than 30 is a good sample. But I'm going to draw one of 100. And you'll see now in this tonight why the size of the sample plays a big role. But I'm going to draw a sample of 100, calculate the mean, and I'm going to say the mean comes out at 68%. I say, the average score for all the students in Australia is 68%. Hang on, how do you know that's accurate? I can say, okay, you know what? I'm going to draw another sample and another sample and another sample. And I'm going to repeat that process 1,000 times. And every time I'm going to calculate the average. And every time, because I've drawn a sample, a random sample, the mean or the average is going to be slightly different. Do you agree?
Yeah.
And that will give me a distribution. And the central limit theorem helped me and say that distribution of the mean of samples, that distribution is normal. It's a normal distribution. And the nice thing of this normal distribution is that the expected value or the average of these normal distributions is the same as that as the population. So I can use that to estimate the population. And I can use the fact that it's normally distributed with certain things to give boundaries. And I can say, if you say to me, but how do I know that's accurate? Maybe it's not very accurate. Okay, I can then calculate boundaries using the fact that it's normally distributed. So let me share the screen and let's jump straight into it. So we're looking at describing a single population, and we're also going to cover tonight chapter 10, which looks at two populations, to compare two populations. We're going to use the same trick to compare two populations. I made the point that we're going to look at concepts of estimation. You need to understand that. We take note of when the population variance is known. We're not really going to look at that. We're going to focus on this one, where the population mean is unknown. And then take note of the rest. I'll go through it, but the main one that we want to look at is this 10.3. And we're going to do the similar thing in chapter 11, where we're only going to look at one section. Okay. So we're going to understand the fundamental concepts of estimation. We understand the difference between a point estimator, and I've given you an overhead of that already, and an interval estimator. And then we're going to look at something called the t-distribution. And again, this is something you need to take good note of, if I want to call it that, because we're going to use the t-distribution instead of the normal distribution because of certain factors which you don't have to worry about too much. But I'll deal with that when we get there. And then you need to understand when to use the normal distribution, which is the Z distribution, and when to use the T distribution. Develop interval estimations. We're not going to look at that one. We're going to look at when the variance is unknown. And then develop an interval estimation of proportions. We're not really going to look at the rest of that. I really want to focus on that bullet point 3. But before we get there, here's a quick overview. What have we done so far? In chapter 1 and 2, in chapter 1, we looked at all the ways one can use business analytics. Did you, in your own life, now that you've got a bigger awareness, come across places where you realize how useful this course is?
Mm.
Can you give me an example, Sharma?
On how to use analytics.
Yeah.
I think just adding up just prices for money. Well, for me personally, using that.
Okay. Anyone else, Tariet, have you used anything that you learned in this course so far?
I use especially for my work.
Mm-hmm.
Yeah, because every day for costing of the things, all the things. Yeah.
Okay. And you?
And I get the average from for the monies and like
Okay.
stops and all the things.
Mm-hmm. Did you say knitting? Are you working at a place that do knitting? Is it?
Yeah.
Okay. Which company is that?
That's a restaurant and a cafe.
Oh, okay.
Yeah.
Okay. Brenda, have you used it in anything? You've got 2-year advantage, so you should have used it for something by now.
Oh yeah, just everyday use like shopping and just the same thing, petrol, fuel prices and stuff, just trying to budget and stuff.
Okay.
Yeah.
Okay.
And
Yeah.
yeah. No. You're right.
Okay, so that's in chapter 2, the key thing that we learned there is data types. Can you, and you, I won't put you on the spot, you know the data types, it's numerical, nominal, and ordinal.
Ordinal.
Yeah. And ordinal we're not going to deal with much, so nominal and numerical, as far as you're concerned, are the 2 most important ones.
Mm.
Okay, in chapter 3, 4, and 5, we learned about graphical, how to show data graphically. And we learned about numerical descriptive measures to summarize data. So how do we summarize data? We can do it graphically, or we can, but can you see that in this case, we've not dealt with anything where we've drawn a sample. This is for a full, this is generally speaking for a full population. But fortunately, we can use those same techniques for what we're busy with now. And then in chapter 6, 7, and 8, we learned probability, the whole probability, and we learned about the variability, and we've learned about distributions. Remember that?
Yep.
And then in chapter 9, we introduced this. From now on, we're going to draw a sample, do some calculations, and give an estimation for the whole population. That's the name of the game. So in the end, we want to come up with probability statements, and you've heard me already talk about it this evening, where I said we want to estimate the average or the mean score for all the students, and we want to say something, it's between this value and that value, 2 values. What is the probability that we write? With 95% certainty, that's a probability. Yeah. Okay. So what we're going to look at first is estimation. And in estimation, we're going to look at just one population, and then later tonight, we're going to look at 2 populations. And then the next step is to look at hypothesis testing, where you come up with a hypothesis and you say, for argument's sake, one school is better than another school. How am I actually going to test that? And it's all working through estimations. Okay, statistical inference. How does it, this is the process. Identify the parameter you want to estimate, and then specify how are we going to do it, and the sampling distribution of it, and construct an interval. So that's the three steps. Decide what you want to estimate. In our case, I'm making the decision for you. We always want to estimate the mean or the average. In this course, we're not going to go beyond that. Estimate what the mean of the average of the population is based on a sample, and then we're going to create an interval estimator. So that's sort of clear as mud, isn't it? We will develop techniques. I'm a slide ahead of myself. For the mean, or another symbol for it is a MU for numerical data, and the population variance, which is or standard deviation. This is sigma square for numerical data. You'll take note of this one. We're not going to really look at that one now. We're just running. It's a fascinating place, but we're sort of running out of time. Okay, statistical inference. A bank conducts a survey to estimate the number of times customers will actually use ATM machines. So they send out a survey, ask everybody, how many times a week are you going to use the ATM? By the way, how many times do you use an ATM? It's interesting how the world changed. I don't think I've used an ATM in the last 4.
I only use it if I'm going to the barbers.
Yeah. But I think because you can do cash out at a cashier, so if you buy your groceries at Coles, you can always say cash out. Okay. The next one is to estimate the mean production time. This is often in manufacturing. They want to know how long does it take to produce the car, or how long does it take to produce whatever product is produced. Okay, and then governments and political parties is always interested in how voters will vote. So they draw samples and so on. I'm sure you've seen them. Okay, the objective of an estimation. So I said to you, we're always going to estimate the sample mean, or we're going to use the sample mean to estimate the population. And this population mean, a symbol, we use a mean, and the sample mean, we use this X bar. This is called an X bar. Yes?
Yep.
And we're going to use the sample variance to estimate the population variance. And similar, we're going to use if we have a population with proportions, we're going to use that to estimate the population proportion. Okay, there's 2 types of estimators, a point estimator and an interval estimator. You should get it by now. Point estimator as the sample mean, and how do we calculate it, or how do we want to estimate the population mean? How do we do it? Draw a sample, calculate the sample mean. How does it look like graphically? Okay, remember, here's the population. Okay, and can you see it's sort of a normal distribution? It doesn't need to be, but it is in this particular case. We draw a sample and we estimate the X bar, or the mean of the sample, and we call this estimation, this mean here. We estimate that that is the population mean. But can you see in this, it's slightly out, isn't it?
Yeah.
Yeah.
And that's what will happen because this sample is drawn randomly. So I now need to find a way to express to somebody that this is my estimation, but it's actually between this value and that value is the population's mean. Okay, so I want to provide an interval. Let me just do this step by step. You do see my screen, huh?
Yes, we do.
I hope so, otherwise if we stuff. Okay. Okay, the interval estimator is affected by the sample. So here's, can you see here, I've now got an interval. I don't give a single point. I say it's between that and that. There's the population. Initially, I don't know the population. I don't know what the real value in the population is. But I come up calculations in my sample and I say, I know the population mean is between this value and that value. And that the parameter is what the population is, and as you can see there, it's included. And I can make a statement that I'm 95% sure this is the actual population parameter. Okay, what characteristics do we want from these estimators? Well, it should be very common sense. It mustn't be biased, so it mustn't always get it wrong. It must mostly get it right, isn't it? It must be consistent. So as the sample size increase, in other words, and it makes sense again, if you think of a population, you say, look, I'm going to take the whole population. Then all of a sudden, you're 100% sure of the average that you calculate. But as the sample size decreases, you get less sure. So that's what they say, it's consistent. I can make it, I can make that more accurate by increasing the sample size. And it must be efficient, it must be relatively efficient. So just a quick thing, an unbiased estimator. Okay, if this is the sampling distribution of all the estimations that I can have, X, I want it to be the same as that of the population. If it was not, if it wasn't biased, mean or the population mean will be there, but that of the samples will be not that. You understand? Okay, hopefully it will come clear when we do some examples. Okay. Now, you just need to know that the sample mean is an unbiased estimator, and the sample median is an unbiased estimator. And the sample variance is an unbiased estimator, and the sample proportion is an unbiased estimator. Okay, it's said to be consistent if getting more accurate. Okay. Mean, there you can see. Okay, now if you look here, the sample mean, we know that the variance of X bar is the standard deviation, the variance divided by N. Therefore, as N grows larger, this variance will go smaller. And the same with the median. But look here, the median has got a factor of 1.57. So that makes it less effective, less efficient than the mean. So we won't really consider this further in this course. The mean, we only focus on the mean. But that's makes the point that the mean is more efficient than the median, although the median is an unbiased estimator. Okay. That's just telling you that, what I just told you. Estimating the population mean when the population variance is known. All this is telling you we make use of the fact that it's normal distributed, the estimate mean. However, I said to you, take note, you can use it when the population variation is known, but that so seldom happens in practice that I'm actually going to skip this. That's at 10.2 that I'm going to skip. So all of this you can skip. How good of me. Okay, one thing you need to know is when you use the normal distribution, if the population variance is known, you use the normal distribution. But as I pointed out to you, the population variance is seldom known. So we don't have to worry too much about this one. Okay. I'm not going to do this example. Okay, this is the one I want to concentrate on. Estimating the population mean when the variance is unknown, and that's 95% of the case we're in this situation. So when we standardize a distribution, when we make it a normal 0-1 distribution, we minus the mean and we divide it by this is the standard deviation divided by the square root of n to make it a normal distribution. Now assume that the sample is drawn from a normal population, or if the population is not normal, the sample size is sufficiently large, bigger than 30. Estimating mu when that is known. So very similar to the Z statistic, which is the normal distribution, we need to use something called the T statistic, or a T distribution. And that's the only thing you really have to remember. For all intents and purposes, you always need to use the T distribution, because we're always going to assume that the population standard deviation is not available. Does that make sense? Okay, I'm going to pause soon, then we'll have a look at that. So you can see it's similar to a normal distribution, but if you compare it, it's slightly wider. Can you see it's slightly wider than a normal distribution? So the student T distribution is the one that you need to know about, and it's slightly wider than the normal distribution. Okay. So when n, which is the sample size, is big, it's very similar to a normal distribution. But fortunately, Excel has got T distribution built into it, so we don't have to worry too much about it. There's the T distribution, and there's something that they have to define. It's called the degrees of freedom. Don't know if they say much about it. Okay, so in your book is a T table, but we're going to use Excel, and it does all the T stuff for you. Okay. Now we introduce a concept called alpha. Alpha is the probability. So we normally work with an alpha of 5% or 1% or 10%. And you'll see how we'll use that. So that in the end, we can make a statement like we're 95% sure that this mean falls between this lower limit and this upper limit. Okay, here they're just looking at how you will look it up if you look using tables. We're going to use Excel, so we don't have to worry too much about it. Estimating the population mean when the population variance is unknown. When is unknown, and if the population actually normally distributed, then so this alpha is 5%, so then 95% confidence interval of that is this value of alpha 2, this T distribution value times this, the standard deviation divided by the square root of n. So this is the little sum that we need to know. I'm actually going to cut and paste this quickly now. I just want to make a cut of this while we're here. Sorry, I'm rushing a little bit through this because I'm anxious to get to using it in Cal, and we can always come back to this a little bit later. How do we estimate mu, or the mean of the population, when the standard deviation or the variance is unknown? Sigma is unknown. Describe a single, what type of data are we looking at? Numerical, type of this descriptive measurement, the central location we want to know, and the population variance is unknown. Determine the sample mean, so calculate the mean of it. Determine the desired confidence level, typically is 95% or 90%, which in turn specify alpha. So if it's 90%, alpha is 10%. If it's 95%, alpha is 5%. And then look up alpha divided by 2, n minus 1 if you want to do it. And then just do a calculation for the lower confidence limit and the upper confidence limit. Okay, let's see if we can do an example. 10.2. If you want to, I suggest that you open it up if you've got access to it.
Yep.
I'm just trying to find mine. Okay. 10.2, XM 10.2. Okay, in the book, you'll see that they're talking of as a Z estimate mean that you can do in Excel. I don't think that option is there anymore. So we'll have to use a slightly different version of it. Okay, I'm just moving my screens around. Okay, let's read chapter 10.2. Anyone got the page number for example 10.2? Oh yeah, it's coming up. Yeah, on page 393. Okay, so this is supposed to be kilometers. As you are probably aware, a taxi fare is determined by the distance traveled as well as the amount of time taken for the trip. in preparing to apply for a rate increase, the general manager of a fleet of taxis wanted to know the distance customer traveled by taxi on an average trip. She organized a survey in which she asked taxi drivers to record the number of kilometers to the nearest 1/10 traveled by randomly selected customers. A sample of 41 customers was produced and the results appear below. The general manager wants to estimate the mean distance traveled with 95% confidence. Okay. Do you understand the problem? So if we apply straight what we want to do, what would be the point estimator of this kilometers traveled?
Are you talking about the upper confidence level?
No, I'm talking of the point estimator. If this is a sample and I now want to estimate for the full population, what will it be? Does that make sense?
Sorry, could you just explain? Yeah, sorry.
Okay. Okay. I want to actually say something about all the taxis. What is the average distance that they travel? So I went out and I drew a sample of 41, and this is the result that I got. So what would be your best estimator for the whole population based on the sample, for the average of the whole population, or the mean of the whole population? Just think logically. I realized I was losing you guys.
Grabbing a sample out of just the 41.
Yeah, I just got the 41, but I want to estimate for the whole population, for all the taxis that's out there and all the trips that they make. What is the average length of a trip? My best estimation will be the average of this lot, isn't it?
Mm.
Does that make sense?
Yeah.
Okay, so I'm going to, first of all, let me just, before I forget, put my little thingy there. Okay, so the bottom line is I want to calculate the average of this. And because I know where we're heading to, I'm going to use the inbuilt formula in Excel that do data analysis, which is the descriptive statistics.
Yep.
And I'm going to say there's labels in the first row, and I want to end up with an estimation. Let's see, identify the technique, and then we're going to calculate it manually, and they want to come up with what percentage to the 95% confidence. If you look at page 394, they want to come up with a 95% confidence limit. See, there's my 95% confidence limit. Okay, so let's do the calculation. So if you put a gun against my head and you say to me, what is your best estimation?
Is that the mean plus the confidence level?
Forget the, all I want is a point estimate. So if I just want one answer from you, it's 7.69. You are right. When we want to calculate a confidence level, and here you can see, so I want to do an upper confidence limit.
Yep.
And that is equal to the mean plus whatever this confidence level figure is here. Okay.
Yep.
And I want to do the lower confidence level. What would that be, Shama? Is equal the mean minus whatever this confidence level is that's coming out here. Let's see if we got the same as the, yeah. If you look on page 394, you'll see we got the correct result. Can you see that?
Mm.
Now, if they've asked in the, so instead of having to do this complex, relatively complex calculation here, I can just use Excel to calculate it, but you need to be very clear on what to do here. So how will I change this if I actually want to estimate, say, a 99% confidence limit? Anyone want to guess? Well, I'm just going into my data analysis again and put in the descriptive statistics. I'm going to put it somewhere else. And I change this to 99%. Okay. Now I want you to, I can tell you now, I'll give you a way. See, it's a question in the exam. Will the 99% confidence limit be wider? In other words, these numbers will, that number will be bigger and this one smaller, or will it be smaller?
Be wider.
Yes, it will be wider because I want to be more confident, isn't it? Remember that. Okay. So, and I do exactly the same calculation. That plus this gives me the upper confidence limit, and equal that minus this gives me the lower confidence limit. Okay, any questions? Okay, are you guys all where I am at, or you still have to do, are you with me?
Yeah.
Yep.
Okay, let's look at 10.53. And I'm going to give you 5 minutes to see if you can do that. XR 10.53. So I'll bring in the data. I'll do the first step and show you where the data is. XR 10.53. The question is, the following observations were drawn from a large population. Estimate the population mean with 95% confidence. What is the required condition of this technique? Use in part A. Use a graphical technique to check the required condition is satisfied. So we want to use exactly the same technique as what I've used here. Can you remember the steps to do it?
Yep.
We go into descriptive statistics, and we keep it at 95%. The confidence level for the mean. First.
Okay, do they want a 95% confidence limit? Yeah. Okay, I'm just trying to open mine. There it is. Okay, so again, to estimate for the population, you want to calculate the average or the mean, and you want to calculate 95% confidence limits. Is that right? So who got the answer?
Yeah.
Harriet, are you doing it?
Yep.
Okay. Brenda, can you do it? Or are you not near a computer?
Sorry. Yeah, I'm trying to do it.
Okay. Okay, I'm going to leave you for a minute, and then I'll be back. What are you guys doing? Anyone wants to share their screen? I'm going to switch off my screen, and then I'm going to ask one of you to share your answer. How's that for a plan, huh? Who's willing to share theirs? In the middle of your Zoom. Brenda, I'm afraid you out because it won't help you sharing your iPhone.
Sorry.
I got 24.4 for the.
Okay, can you click on, there's a share screen button on your Zoom at the bottom. It's a little green button. Can you see it?
Yep.
Click on it and share your screen. There you are. Okay.
Easy. All right.
So click on that. Click on the 24.4. I just want to see the formula. Yeah, that's not too difficult, is it? Except you've got it wrong.
Sorry, I meant to put on the main.
So upper confidence level is 24.0099.
Sorry, what did you have?
Upper confidence level is 24.0099.
Okay. Yeah.
And the lower one is 21.1900.
Okay. Double click on your D19. Yeah, that one you've done right.
Yeah.
Okay. So how difficult was that?
Not very.
It's easy.
Okay, but my question is, do you really understand what it means?
Yeah.
So let me, okay, stop your share. Okay, and I'll share my screen, and I'll try and use some of my squonky drawings to explain it to you a little bit. So let me just think. Okay. Remember now that although this is actually using the T distribution, Excel has got it built in to use the T distribution. Why do we use the T distribution? Because the population variance is unknown. If it was known, we would have used a Z distribution. But as I said, that's seldom true, so let's never even consider that. Have I shared my screen? Or not yet?
Yeah.
You can see my screen? So
Yeah.
what I want to say is it's always good to draw on a piece of paper or somewhere your normal distribution and just check what you say. So I'm going to just draw it here. I'm getting better and better at this. Okay, so there's my normal distribution. What this says to me is, what does it say to me? Insert. I'm effectively now saying I estimate if, yeah. So I've got one of these. And if this is the actual population, the distribution of all the values in the population, I've now drawn a sample, and here's my sample, and I've now calculated the mean, which we know will be right here in the middle. What was that mean that you got in your
20.
22.6.
22
Oh,
points?
22.
Yeah, okay. Now the actual mean of the population is, we don't really know what it is, but according to my drawing, it's here, but we don't know. So I want to put a boundary around this, or a interval estimation, so that I can say with 99 or 95% certainty, these boundary values will cover the population's actual mean. I don't know what it is. I estimated 22.6, but I want to be with 95% certainty tell you it's going to be between this value and that value. What did you calculate as the lower confidence limit?
21.1.
21.1. And what did you calculate as the upper confidence limit?
24.2.
24.
Yeah.
Okay. Can you see that because the way we calculate it, this is always in the middle of these two boundary figures? And can you see that the actual population mean in my drawing is actually between those two values? And we know that will be true 95% of the time, because that's how we actually did this calculation. Is it clever? Are you? I'm always a bit impressed with how good this is actually. Okay, so let's see if what did they do in the slides. Okay, so there's our data. To describe a single population, we're starting off with the data type is numerical. So the moment we know that, we know we're going to use the average or the mean, and the population variance is unknown. So we replace that with S, which is the standard deviation. And we're going to do this calculation, but fortunately Excel does it all for us in one go. Happy with that?
Yeah.
So let's see. Yeah, instead of us doing all of this calculations, Excel has done it all. All we had to do is put in the data, and it comes up with this confidence limit of confidence limit one. Okay. What is the actual population? Yeah. So it's 7.7. It's 6.77 kilometers plus 8. Okay, lower confidence limit is 6.77. Is that what we got? Was this the wrong example? Is this what you guys got? 6.77?
I got that at 90% confidence level.
At 95% confidence
No,
level?
I got for upper confidence level 8.4 and lower confidence level 6.0. I got that for confidence level at 90%, not 95%.
Sorry, we're looking at the wrong thing. I'm looking at the previous problem that we had. Okay. Okay. I'm looking at XM1002, this one. Can you see that's the same
Yeah.
we got?
Yep.
Okay. Nearly compared the wrong one. Okay. You can see here did any of you manage to install this CourseMate Express for business statistics? I could never make it work, so I've just ignored it for the moment. But the current version of Excel has obviously got it in, and we've now used that. Okay, so there they go, interpreting the results. So I hope I'm repeating now. We estimate that the mean distance traveled by the taxis lie between 6.7 and 8.62. And the general manager can use the estimate to determine the effect of different pricing policies. It's worth noting that the accuracy of the interval estimate is dependent on the validity of the sampling process and the distribution of the distance that are required to be normal. Okay, so how can we check for normality? That's a good question, because that's question B of the one that we're looking at. What is the required condition? It needs to be normal. And how can we check whether data is normally distributed? Anyone got an idea? We draw a histogram of the data. Anyone know how to? I'm sure you can do it all. Okay, you do it on your side. I'll do it on my side quickly. Draw a histogram of the data. How do we do that? We use a pivot table. My recommended way of doing this is use a pivot table, drag in the data, change the data here. Instead of sum, it needs to be count. Let's see who's first. Tell me when you're done. Then group this. Group. I think we'll just make groups of 2. A bit of a problem here, I think. I would say this is not normally distributed. I'll be very dubious about these numbers. Can you see that this is not normal distributed?
Yes.
Okay, so let's go and look at the other example that we've done, this one here. I'm just going to check if it's normally distributed. I won't ask you trick questions. If I give you these types of stuff, it will be normally distributed to the extent that I want it to be. So I won't trick you, okay? I'm just not a tricky person. Okay, 2, 1, 2. If I plot this now, we think this is normally distributed. Okay, this is quite normal distributed. It's got a sort of a point in the middle. I'm not going to format it any further. You guys know how to format. So that's the check whether something is normally distributed. That's the check that you can run. Okay?
Yes.
Theory, if you do this in practice, you need to check that it's normally distributed. Checking the required, at the beginning of the solution, we said to use the t-distribution, we assumed the population is normally distributed. Now, we need to check it. How do we do it? We plot a histogram data set using Excel, and that's the data shape they got. Mine is slightly different, not sure why, but it's normally distributed. Okay. Okay, let's take 5-minute break. Okay.
Yep.
See you in 5 minutes.
Yeah.
Right on. Right on. Okay, so are you guys back?
Yep.
Yep.
Oh, yeah, this year. Brenda, are you back? Do you guys want to do another example of the point estimation or the mean estimation and the upper control limit and the lower control limit? Were you good with that?
Oh, is it called control? I thought it was upper confidence level.
What did I call it now?
Upper control.
No, you're right, it's confidence. I'm thinking of, there's another statistical technique which is called control, then it's called control limits. But in this particular one, it's confidence limits. Sorry.
Okay.
My bad.
No, okay, that's okay.
So if you get an exam and it says control limit, you know I've done it wrong again. No, it's upper confidence limit and lower confidence limit. Okay, proportion. You remember the old classic example where I draw beats and there's red beats and white beats? That's when you deal with proportion. Now I'm just going to basically skip through this quickly. You use the same technique. You calculate, whenever you do, you draw a sample and you calculate the proportion in the sample. And that is the estimation of it. If you want to calculate the interval in which it falls, you can use a similar technique by that plus or minus. In this particular case, it's a normal distribution, and I don't know if you can remember, but to calculate the standard deviation of a proportion, it's P times Q divided by P times Q is the standard deviation. Is the variance. If you want to calculate the variance. Anyway, take note if you someday get a job where you have to calculate the proportions, look it up in the manual. There it is. So I'm not going to go through any of this. Okay, there's one other bit of a topic which always comes up. How big must my sample size be? Now, my simple answer is, how much money have you got? As big as we can within the money that we've got. But you can see here, you can use these calculations and sort of reverse it and get a big sample size, make the sample size bigger or smaller. You can just put in the numbers into this calculation and then it will give you how big the sample size must be. Does that make sense? I'm not going to go into that either. It's not for this course. Okay. So that, let me just see here. Here's a nice diagram. If I make a good note of this. If the data type is numerical, I want to estimate the central location. I use the T estimator of me and do it. If the data is nominal, that means proportion. I use a Z estimator. But the key one we're looking at is this one here. Okay, that is effectively chapter 9. So in chapter 9, if you want to know chapter 10, sorry. Chapter 10, the important ones is 10.1 and 10.3. You're making notes.
Yep.
10.1 concepts of the estimation. We're not 10.2. 10.3, calculate the mean and the variance is unknown. Take note of 10.4, take note of 10.5 and 10.6. Okay, but 10.1 and 10.3 is the two that we need to look at, or that you need to focus on. And by the way, this exam quiz 3 includes chapter 9 and 10. So chapter 10 and 11. Make sure you have studied that as well before you start the quiz.
And is that including just the same stages in chapter 9 and 10 that you talked about? So not including 10.2, just
the quiz exam, the exam quiz has got some multiple choice questions. So there might be something that counts 1 or 2 points from the other sections. But the
okay. Yep.
part is 10.1 and 10.3.
Yeah. So so it's best just to study both chapters fully.
Yeah, but just make sure you've studied that already.
Yep. Yeah.
We'll start the quiz. Okay, I'm now going to look at chapter 11. And chapter 11 is the same thing again. We're only going to look at section 1 and section 3. I think I'll clarify just now. Let's see. Okay, I'm just getting chapter 11 out. And by the way, you'll see in the course material, I've done 2 videos. One that does the very examples that we've done here, showing you exactly how to do it. Okay, it's coming. There we are. Okay, one thing that is often needed in the statistical world is to compare 2 populations, 2 or more populations, but we're only going to stick it into 2 populations. And again, we coming back to, I don't know what's happening now, but let's see. Again, you come to the point where you've got 2 populations. You want to draw a sample from each of the populations, and then you want to a point estimation. What kind of point estimation do we always do? The mean. We only worry about the mean, the average. And then we want to do, for each of the populations, we want to do that. And then we want to do an estimation of the difference between the means. If the 2 populations are the same, the difference will be 0. If the 2 populations are not the same, they will differ. And again, we can have confidence so that we can give a confidence limit around this estimation that we have. Okay, let's look at an example problem. Okay, we're going to concentrate on the population mean and the difference between the 2 population means. That's what we're interested in. We're only going to look at it when the variance is unknown for the two populations. Okay, let's look theoretically. We now know that the sample distribution of the two populations, bar x and bar x2, bar x1 and bar x2, will look something like this. It will again give us a distribution. Can you see if I calculate the average of the one population and I minus the average of the other population, and I draw two different samples and I calculate this is the same calculation, I'll end up with a distribution of answers like this. Do you agree? And the expected value of this me1 minus me2 is 0. If these two populations are exactly the same, I expect this value to be 0. Do you agree?
Yep.
But if they differ, this value will be differing quite a bit. And then, so again, I want to be 95% sure they're the same or not. So here's the thing, two independent random samples are drawn from two populations. Because we are interested in the difference between the two populations, we use the sample statistic x1 minus x2, which is an unbiased and consistent estimator of the population parameters me1 minus me2. Hopefully it will become clear when you see an example. Okay, either this calculation, the difference is normally distributed, in the original population distributions are normal, or it's approximately normally distributed, and the expected value of x2 minus x3 is that, and the variance is this calculation here, is the variance of, the variance of the one divided by the size of the sample plus, and this is interesting, it's plus. So if the one population varies this much and this much, then you actually have to add the two variances together. Does that make sense?
Yep.
Okay. Now, if the variance is known, we can use a Z statistic. That is what we say. I'm not going to focus on that because it's seldom true that that's unknown. Okay, and so they work through all the calculations, which you don't have to worry about. And then they work through an example, which you can worry about if you want to, but you don't have to. Okay, and they do the whole thing. Okay, let's get to 11.3. Okay. Okay, 11.2, sorry. So in this particular case, we're interested in 11.2, and that's the only section we're really going to look at. And you can take note of the other sections. Did you make a note of that? 11.2. And take note of the rest. Read through it and so on, but
11.2, did you say?
beg your pardon?
Did you say 11.2?
Yeah. This is the one we're focusing on.
Yep. Thank you.
And again, we're going to use a T statistic, and we're going to use the sample variances. In Excel, it's very simple. If you do it manually, it's less simple. And they explain to you how we're going to use the sample variance. But because this is unknown, we have to use the T distribution and not the Z distribution. So it's the exact same story. The two unknown population variances are equal, and sometimes they're not equal. We're not going to worry about that either. This is the one we're looking at. Now, we want to look at case 2. Getting there. Okay. The two variances are unknown and they're unequal. And we want to construct an interval estimate. And here is the degrees of freedom estimation and so on. We don't need to worry too much about it because Excel does all of that. So when do we use this technique? When we want to compare two populations. When our data is numerical. What we want to estimate is the central location, which is the mean or the average. And the population variances is unknown and potentially not equal. Experimental design is independent samples, and the population distributions is more or less normal. Okay, XM1103. Let's go and look at that, shall we? Do you want to open that on your computers? Come on. My computer is very sluggish tonight. Not sure why. Are you going to follow along?
Yeah, it was 11.3, was it?
I think it's 1103. XM 1103. Yeah. Have you guys opened it?
Yep.
Yep.
Okay, there's mine opening now. Okay, so let's see. This is sort of an example. There's 30 people were randomly selected and asked what they regularly ate for breakfast and lunch. Each person was identified as either a consumer or a non-consumer of high fiber breakfast cereal. And then the number of kilojoules consumed at lunch was measured and recorded. This data are listed below. Estimate with 95% confidence the difference between the mean kilojoule intake of the consumers and non-consumers, assuming that the two consumption populations are normally distributed. Okay, do you understand the problem? These are people that eat breakfast cereal, and these are people that don't eat breakfast cereal. And the theory, the thing they want to test, they say people that eat breakfast cereal eat less for lunch than people that don't eat it. So it have an impact on diet. Who think this is right? You should eat cereal for breakfast and then you eat less for lunch. Who think that's true?
Yeah, that's true.
You think so?
Yeah.
Or in the morning, and you eat less than lunch. Yeah.
If you eat cereal in the morning, you eat less for lunch, as opposed to eating something else, I guess, for breakfast. I think that's what they're trying to say. Okay, how I'm going to go through it, just do it with Excel. So what data. So we know it's numerical data, and we know we want to compare two populations, and we know that the variance or standard deviation is unknown. Okay, so paired for two samples, paired, it's not a paired situation. Two sample assuming equal variation. No, we don't assume equal variation either. do we want to do 2 sample assuming unequal? And can you see it's a t-test? So which of those 3 should we choose?
Two sample assuming unequal variance.
That's right. The second one from the bottom. That one. Okay. You're right. If you do that in the exam, you'll win.
Okay. So how come it's unequal variance again?
Well, you can see here's 2 populations. There's no chance that they've got the same variance, is it?
Yeah.
Okay. So highlight the first plot. Highlight the second plot. Click this thing that says labels. We expecting the difference to be 0 because you'll see next week when we do hypothesis testing, we always assume that the difference is going to be 0. Okay, just believe me. Alpha level, what did they say here? They work on alpha 0.05, so that's correct. And I want to put it on the same data set. So I'm going to put it there. Click on OK. Okay, and here's our data done. Okay, so first of all, I can now do a calculation. And it's very good to initially always do this. So do the means differ? I put non-consumers high because that's what the test tells me. I'll put them first. So yes, there is a difference on average of 261 kilojoules or grams or whatever they measure. Are you happy with that? So I calculate that difference. Now I want to calculate an upper control limit and a lower control limit. Now I draw my, okay, and upper control limit, I'm just going to, is this difference. Let me just think about it.
Is it plus the value of the 2 tail?
Yeah, I think, but I'm not, I think there's a multiplication. I think it's times the variance. Just quickly have a look here. Yeah. I'm just going to go to the slides so I can bring in that particular calculation. I just want to make sure we get it right. Otherwise, I show you the wrong thing. Okay, it's this one.
So would it the difference between the 2 means values minus the 2 tail value times the square root of the figure 1 divided by figure 2 plus figure 2 divided by figure 2?
Yeah. Okay. Just give me a moment. I think you're right, but I just want to check it. And the easiest way for me to check it is to have this formula right there. Okay. Okay, so this x1 minus x2, this is nothing other than this value here. Okay,
Yep.
plus the critical to tail. That's what I don't understand. Okay, I'll try. I think it's this one, critical times the square root of the standard deviation of the first population, or the variance, that one, divide by how many were in this 10, divide by 10.
So to do the square root, is it just that SQRT?
Yeah, SQRT, that's right.
Right.
Plus, and the same thing for this population. This one, divide by that one. So this is slightly more complex than the previous round. Yeah, and this will be the same thing, but for the other side. So instead of yeah. Okay, the lower confidence limit is the same story, except that I minus it. Instead of plussing it, I minus it. So it's between 28.75 and 493. And one thing to always check, does this fit in the middle of these two numbers? So it's, for instance, when I have to grade you and I don't exactly know what the data is, I can very quickly check, is this number in between these two numbers? Is it as clear as mud?
Yeah, I'm just trying to practice the formula of the
I'm going to draw two histograms for these two, and then let's see if we can make sense out of it. Okay?
Yep.
Or, okay, first, yeah. Okay. Let's see. No. Insert, pivot table. Okay. Draw a histogram for consumers. And this needs to be changed to count, not sum. And we want to group this. Oh, come on. Now, why would Excel do that to me? Okay. Can you guys do it on your machine? Let's see if I can do it for non-consumers. Yeah, it works for this. So start at 2000 and go to 900 in hundreds. Okay. Yeah. Okay, let's see, insert. Okay, that's how that one looks. I'm just going to make this 200 in groups of 200. Okay. Make a copy. Let's see if I can get it right now. Non-consumers, non-consumers, consumers, consumers, count. It's because there's blanks that it doesn't want to group. Just so. So I'm going to remove blanks. Group. Okay, I'm determined to do it, so I'll just insert pivot table in sheet 4, listing sheet. Okay. Okay. Do you see it didn't want to do it because there's blanks in it? So I just did the pivot table now. I just selected data without the blanks and hopefully it will do it now. Let's see. Yeah. So I'm going to start at 2000 and go to, what did we go in the other one? 2006. 600. It's okay. And steps of 200. Okay. The reason I'm doing this is to show you how two populations compare with each other. Can you see that this 2,223 yeah, can you, if I have it about like that, this one needs to be much wider. So if I compare the two populations, and I make this one 2,600, this one, and I scale it, try and scale it the same. Okay, can you see that this 2,400 to 2,600 is in line with that one? And this one is in line with each other, and this one is in line with each other. And can you see, if you just look at your eye, would you say the average of this one is higher than the average of this one?
Yep.
Yep.
And if I now use my mind's eye and I actually put in, we know this stuff is sort of, our theory tells us we're going to use something like a normal distribution. So I can now draw my normal distribution across this lot, and I know it will look something like this. Where this one will be significantly narrower. So what this in theory says, am I 95% sure that the difference between this mean here and this mean, this difference is bigger than, so if I draw two lines, let's just draw. Does these drawings help you guys, or is it just confusing you? Does it make sense?
No, it's helping.
Yeah, so
So what we've done with that calculation is ask ourselves, is this difference from this population mean to this population mean, is that bigger than 0? Is it, for instance, if this whole population was more towards the right, then we might not have drawn that conclusion. But we can now see in our calculation here that yes, it is bigger because 0 is not in this interval. Can you see that? So what do we say? We say we estimate the difference is 261 gram or 260 kilojoules, whatever they're talking about. Let's see what they're talking about.
hey Francois, I actually got 264.4 for the upper confidence level.
How did you do that, mate?
Um,
Look at my formula. Is that the formula you've got?
Square root. Yep.
I don't know how you. Did anyone else do the sums, and what did you get? Taria, did you do it?
Yeah, but I've just done the lower one. Upper one is not coming because in my difference it's showing a minus 261.2 in the difference between two means.
Is yours a minus here?
Yeah.
Well, just reverse it around so that you subtract non-consumers minus consumers.
Okay.
Is it right now?
Just a second.
Shama?
Yeah, sorry, I had it on the P2 tail. I just moved it to the T critical 2 tail. And I was,
So this is the one we want.
yeah.
It's worked now.
Yeah.
I'll make it clear.
I got 493.6. Yeah.
I'll cut and paste this. And it's sort of for myself a memory thingy. Creating my own memory hook now. This value there is the equivalent of that. Okay, does that draw a picture for you? So this T alpha divided by 2 is that number there. If you look at a T critical 2 tail, T, yeah. Okay, so this gives me the numbers and it says, yes, it's true, and if I draw two histograms, I can compare it, and I can also see, yep, they definitely two different populations. Although there's quite an overlap, they are two different populations. Okay, so we do another exercise on the same, or let's just quickly look here, what they've done, and then, okay, they talk a little bit about the t-test and so on. Let's see what they got as an answer. There's the data. There's the calculations that they've done. And they then come up. Okay, they've done it all in the negative. Okay, but that you can see that that's just a sign, whichever way you want to do it around. Does that make sense?
Yep.
Okay, so example 3, interpretation of the results. By the way, this interpretation is something that I'm going to look at quite strongly, because that's business analytics is about how do you interpret what you do. So the difference in mean kilojoule intake between the consumer and non-consumer is estimated to fall between this value and that value. That is, we estimate that non-consumers high fiber cereal eat on average between 29 and 494 kilojoules more than consumers. So people that don't eat high fiber eat 29 to 494 kilojoules more than those that do eat. Okay. And here's the actual calculations similar to what we've done. But some of this, yeah. Anyone got any questions on this? So what does it? The problem objective is to compare two populations. So the moment I say to you, compare two populations, you know, it's the t-test, data type numerical. We want to measure the central location. The population variance is unknown, and it's independent samples, and the population distributions is more or less normal. Okay, let's work through example 4 together. It's on page 435 if you want to. Okay, I want you guys to do it, and then I'm going to ask one of you to share the screen and walk us through it, okay?
Is this in the chapter 11 data?
Beg your pardon?
Is this in the chapter 11 data?
Yeah, it's XM 11.4.
Right, thank you.
You'll see it. There's on my screen is chapter 11 data sets at chapter 11. And you can, it's on Moodle, so you can get it on Moodle, but I thought you got it already.
Yep, you got it, yeah. XM 1104.
Brenda, did you get it?
Yeah, I got it.
Okay, I'm just closing some of my stuff here. I'm just trying to get rid of this spreadsheet I'm working on. Okay. Tell me when you're done. Okay, I've got some good news for you after this, so let me know when you're done. Okay, so we've again got two parts. Who wants to share their screen? Let me switch off my share. Who's ready to share? So the problem here is a national known manufacturer of replacement shock absorbers claims that its products last longer than the type of shock absorber that the car manufacturer installed. To examine this claim, researchers equipped with cars with original shock absorbers and another 8 cars with replacement shock absorbers. The cars were driven until the shock absorbers were no longer effective and the number of kilometers traveled before this occurred to record. The results are shown in the following table. Estimate with 90% confidence the difference in mean kilometers traveled until the shock absorbers fail between the two types. Who's going to share?
I haven't got it, so.
Are you going to share?
No, I haven't got it, so.
I'm on the, I have it done, but I'm on the iPhone. So can I tell the answer?
Okay.
Sorry.
Okay. It's okay. I really recommend that each of you guys do 3 or 4 examples literally before you do the exam. Okay. Do you hear me?
Yeah. Yep.
Before you do the quiz exam.
And that's in chapter 10 and 11.
Yeah, chapter 10 and 11. These same examples that I've done with you, make sure you can do it. Okay, so I'm going to show you quickly how to do it. It's very quick. You just click on data, go to data analysis, go to which one should we choose?
Equal.
To unequal variance.
This one. Yeah, make sure you choose that one. Okay, in what should we check? Let's see what we've got here. No, that we want to do that one. And we want to do that one. Okay, hypothesis mean difference is 0. Labels is 0.05. Output range, I'm going to put it here. Okay, is this right?
Can you share your screen?
Oh, I'm not sharing. Okay. Gone. Okay. Thank you. Okay. Coming up, my screen. Okay, so you can see I've filled in, I've went to the t-test 2 sample assuming unequal variance. And I put in this and I filled in hypothesis mean difference is 0. I ticked labels and I put the output range. Is there anything else I need to change? It's a trick question.
No.
Hypothesis mean difference 0.
You read it. If you read in the book, it says estimate with 90% confidence. So what must I change?
The confidence level.
Where's the confidence level?
The mean difference. Hypothesis mean difference.
No.
Alpha?
Say again.
Alpha.
Yes. What must it be?
95?
No.
Uh,
To get a confidence limit of 90, which is what they ask, this
Right.
alpha needs to be 0.1. Go and read about it a little bit in the book if you want to. So now I can do my upper control limit, and my lower control limit. First of all, I calculate the mean difference equal. I always take the biggest one minus the smallest one, and then I know it's positive. Okay? And in my interpretation, I now know that it seems that the replacement one is higher than the original, and that's what I want to test, isn't it? Okay, I wonder if I still got that formula here. Yeah, no, I haven't. Okay, but we now know how this works. It's equal that plus this one,
The T, right.
yeah, times the square root of the variance
Variance.
divided by that one
Observation.
plus
Plus the variance of
that one
the replacement.
divided by that one. Okay.
I got negative 0.7.
Okay, I'll check you out just now. No, it should be 6.38, between 6.38 and 13. Just check your formula again against mine. Oh, no. Looks
Minus.
like, yeah, looks like, let me just check my formula. Oh, this one. Oh, there. No. Okay, that's right. But this should be minus.
Minus, yeah.
That's what you said. I deliberately made that mistake just to see if you guys. Okay, so if I want to do it negative, like if I want to get it the same as the book, all I have to do is do this minus this one. And then these two swap around. No, that's still my lower control limit. Yeah. So in my interpretation, I can just say that the original is -7 worse than the replacement one, and it's between these values. Does this include 0? No, it doesn't include 0. And you can see I'm going to do the histogram. Obviously, this won't draw massive histogram because there's very few data points. But let's just see if our theory works, if my theory works anyway. Original, change it to count. I'm going to try and just get 3 group from 27 to there, make it 5. Yeah, and insert graph. That's quite a nice, neatish, normalish one, isn't it? Okay, now I do it same for the replacement. Change the sum to count. You do understand that I just do this to demonstrate. So 27 to 52. And I'm not going to spend a lot of time now, but the 2 is about like this. Can you see if I line up 32 with 32.5 and so on? Can you again see that you have a feeling this one is higher than this one?
Yep.
The average is higher than this one and this one. So I'm not going to go through it again, but there you've seen another example. Okay, let's have a 5-minute break and then I'll talk to you about the assignment. Okay, last stretch. I'm going to do exercise 11:18. And I'm just going to do it from start to finish. Okay, the question is, the managing director of Tasty Incorporated, the baby food producer, claims that her company's product is superior to that of a leading competitor. It's on page 439 if you want to follow, 11:18. Because babies gain weight faster with her product, to test the claim, a survey was undertaken. Mothers were asked which baby food they intend to feed their babies. Those who respond Tasty or the leading competitor were asked to keep track of their baby's weight gain over the next 2 months. There were 15 mothers who indicated that they would feed their babies Tasty, and 25 who responded that they would feed their babies the leading competitor's product. Each baby's weight gain in grams was recorded, and the data, and there's the data. Estimate with 95% confidence the difference between the mean weight gain of bodies fed the 2 products. Check to ensure that the required conditions is satisfied. Okay? Any questions? So what's the first step? We need to decide which test to do. Yes, it's a t-test because the variance is unknown and because it's the only test I taught you. Can you see my screen?
Yep.
Yep.
No. I see the missed competitor.
Did you say the confidence level was 90%?
95.
No, it says in the book 95%. Okay, so to do it very quickly, I go to data, go to data analysis, go to test 2 sample, assuming unequal variance. Highlight the first column, highlight the second column, I expect the difference to be 0. My alpha is now not 0.1 but 0.95, no, 0.05. And my output range, yeah, that's good enough for me. Click on OK. Difference. Okay, as I said, I always make sure that one is bigger than. Oh, can you guys see a problem? Who sees a problem with my solution? I must have missed. I must have missed that, and I missed the
competitor.
Yeah. So let me just do it again. this one, I didn't select competitor. Click on OK. Yeah. Okay, so that's the difference. My upper confidence limit equals the difference plus this one times the square root of this divided by this plus this divided by this. Oof. Okay, I need a bracket at the end. Thank you. That's what I get as my upper control limit. My lower control limit is basically the same thing with a minus. Okay, so again, my estimation is that babies gained on the tasty one. I can see the tasty is bigger than the average than that one. So on the tasty one, they gain between 3 and 8 kilograms. Okay. Taste at 90% confidence. Babies tasty will gain 8 and 3. Okay, then it asks the question, check that the assumptions is correct. What is the assumptions? The assumptions is that both of these two are normally distributed. So I'm checking the first one, insert pivot table. The group, I'm going to round this down to 25 and round this up to 45 and make this groups of 5. That seems to make sense. Let's see. Yeah. And I can insert the graph. Yeah, that looks pretty normal. What do you think? And I'm going to do this one. Existing worksheet on sheet 2. And drag competitor, change it to count. And this one was 25 to 45 in groups of 5. I'm going to make the same here. 25, 5 to 45 in groups of 5. Insert, graph it. Scale it so it looks the same size. Yeah. Can you see that they're checking the assumptions? Yep, it's more or less normally distributed. And again, I can see that this one is smaller than this one. Can you see that? The average will be less than that one.
Mm.
And that's what we've got. And yeah, the overlap isn't big. If you look at the mode, can you see this mode is in 35 to 39, and the mode here is 30 to 34. That also tells me there's a difference in the average or difference in the means.
Does it matter what we group by?
They need to be the same if you want to compare it like this.
Yeah.
Yeah. Does that make sense?
Yeah.
But it doesn't really matter. I try and get 4 or 5 or 6 groups when I do this type of thing. So if you an exam says check the underlying assumptions, that's what you need to do.
Yep.
And you need to make a comment that says the populations are reasonably distributed or something. Okay, I think we've right this one now to the end. You now know how to do the calculation for a single population or a single sample and extrapolate that to a population, and then you've done it for the other one as well. Okay, now after lots of churning around and having great fun analyzing the coronavirus, which I've shared with you guys, I've actually decided to make the assignment less complex. So the assignment will not be on the coronavirus data, it will be on other data. Who's sighing there?
I am, because I've done some data on it.
Really?
That's right.
So you'd send
That was
it,
fun.
send it to me, I'll let it count in your favor, okay. Oh, sorry, yeah. If you want to stick to it, that's also fine, but you'll see the other assignment is far less complex. Yeah. What do you want to tell me what you've done, Tariet, or show me what you've done? I'm impressed.
No, I think it's Brenda.
No, that's me.
Oh, sorry.
Brenda.
Brenda, was it you? Sorry.
Yeah.
What have you done? Do you want to send it? If you feel like sending it to me, or put I'm sure you've learned a lot.
Yeah, I've learned a lot through doing that. That's fine. I'll look into the new what you have for the assignment.
And I'll open it up tomorrow. And I think it's more realistic for business analytics course than. Well, you've seen it can get very complex very quickly. And the other thing is that the new one I've got have some of this application of this chapters in as well, which is what I wanted to cover. Okay. Okay, let's see. We haven't done this one. But yeah, you can see they've also done the distributions, checking for normality. The distributions are not well set, but they seem to be approximately normal since the techniques are robust. We can be confident about the result. Okay, there is another type of experiment where it's called matched pairs. We're not going to look at that, but there is different ways of analyzing that, which makes it very good.
So we're not looking at 11.3?
Say again.
Oh, I was just checking on the chapter outline, and seeing if we weren't looking at 11.3.
Let me make it clear. Not looking at 11.1. We looked at 11.2.
Yep.
And we're not looking at 11.3. And we're not looking at 11.4. I suggest you read through it and take note so that if you have a problem in that league in future,
yep,
you need to know where to get it.
Yep. So I'm just clarifying, we're only looking at 11.2, 11.4. I mean, sorry, 11.1.
11.2.
we are not looking at 11.1. Not.
Oh, okay. Thank
We
you.
are looking at 11.2.
Thank you.
But I do suggest you read 11.1 and 3 and 4. Just read through it so that you know what's going on there. Or just take note of it.
Mhm.
Okay, is there anything that you guys want me to review or revise anywhere in the course that you don't fully understand or feel not confident about? Okay, I think then we've finished for tonight. Have a fantastic time. You know, I'm contactable. You can set up one-on-one Zooms. Some of the other students did take me up on that, and I think it worked fantastically well. So if that's what you want to do, you can obviously do that. I'm available for that. I take phone calls. You can email me work. I'll look at it and make sure it's correct and so on. So please, you know, while we in distance education, and some of you I would have been in class, make use of other capabilities that this allows us to do. Okay.
Okay. Thank
Hey,
you.
Francois, so just clarifying, those three examples that we did of the T distribution, are those the ones that you want us just to practice for the exam, the quiz 3?
Well, you're obviously not going to get exactly those ones. All I'm saying is there can be, because we covered that in the work, isn't it?
Yeah.
There can be examples where you have to compare two populations with each other, or do statistics on one population.
Yep.
Okay.
Thank you.
Thanks.
All the
See you.
best. See you, Brenda.
Thank you.
Thank you.
Bye.
See you next week.
Bye.
See you.
Bye.